Hello. In week 5, I'm going to cover essentially two topics. The first thing is we're going to look at graphs of functions and determine what the corresponding derivative function would be. And likewise, I'm going to show you that if you see a derivative graph, how to go back and see what the original function looked like. The second part of this week will be stepping away from the theory of the derivative. We've been looking at the definition of the derivative, and we're going to start moving away from that theory and into some of the easier to digest, maybe, formulas. I'll start off with a little housekeeping. Going back to week 3, I had a couple of questions about the composite function theorem, and if it didn't make sense to you, there's a reason for that. There was a typo in the slide. Originally, it said that the limit as x approaches a of f of g of x is equal to f of the limit of as x approaches a of g of x. And that makes sense because we can, as long as we have continuity, we can just take the limit and move it inside to the inner function. But the result of it shouldn't be L like it previously stated. It should be f of L like it shows in the example. So apologize for any inconvenience that that may have caused. In this first example, this first graph, the important thing that I want you to recognize is that this is a graph of f of x, just the regular non-derivative function. And therefore, I'm going to label the y-axis as f of x. And I'm making a big deal of this because I want you to get into the habit of looking at the y-axis to determine if you're being given the f graph or the f prime graph. Now, in the instruction, it's telling us to find the f prime graph given f. And now the strategy for doing that, and again, I'm making a big deal of the word sketch, and you'll see why in a minute. First thing you're going to do is directly below this, you're going to sketch another xy plane. It'll look like this. And then you'll label it, label the x-axis with x, and label the y-axis with f prime of x. So the reason that we're doing this is because you want to line up all the x values in order to be able to effectively sketch the f prime graph of what's given to you. Now, step 2, you're going to determine first where the slopes of the tangent line, okay, because remember f prime, this is the derivative, and we put the concepts together that slopes of the tangent line are the same thing as rate of change at a particular value of x or an interval of x. And they're also the same thing as the derivative. All three of those are the same thing. So you want to determine on this graph where the slopes of the tangent line would be 0. Now, the thing to know about this is the slopes, when the slopes of the tangent line are 0, that means that they're horizontal lines. Well, that's going to happen here and here. Then for step 3, once you've identified those values of x, and you don't even have to know if this is x is equal to 5 or x is equal to 100. You just need to know where it is on the graph. Now then in step 3, you're going to plot these on the derivative graph. If the slope is equal to 0 and you're plotting the derivatives, well, that means that the derivative here, or f prime, is 0. It's essentially like this is just going to be a plot of all the slopes of the tangent line. So slope of the tangent line here is 0. That means f prime is 0 at this value of x. And again, we don't need to know what the value of x is. That's why it's a sketch and not an actual graph. Now, same thing here. I'm going to mark the x-axis here with a point. And then next thing you're going to do is you're going to look around these. So we have an interval here, we have another interval here, and another interval here that are between the two places where the slopes of the tangent line are 0. So we're going to look on either side, let me just say that formally, to see if the slopes are positive or negative. And now looking here, anywhere until from negative infinity, when x is equal to negative infinity, to this point, if I draw a tangent line for any of these values of x, see how the slope of that tangent line would be negative? So I'll mark that with a negative. And then once we get past this, where the slope of the tangent line is 0, we get past that from here to here. Any place that I can draw a tangent line on this part of the graph, all those slopes of the tangent line will be positive. I'll mark that. Oh, well, I'll mark that in a second. All right, so let me just say formally. So when the slope of the tangent line is negative, the y values for f prime are going to be negative. Okay, and see what happens here. Now, as far as the direction, watch how this goes. We know that this is exactly 0. And then if I drew a tangent line, say here, you can see how it's negative, but it's not very negative. It's just a little bit bigger than 0. And then they just gradually get steeper and steeper and steeper. Well, this, in other words, the slopes, they get to be bigger values, but just negative. So you can see that the graph of f prime reflects that. I'll just kind of show you that again. Okay, so now going back to here, we said that all the slopes of the tangent line between here and here are going to be positive. And therefore, when that's the case, the y values on the f prime graph are going to be positive or above the x-axis, right? Because here's the positive part of y. And again, think about the pattern here. It starts off where these slopes are just a little bit bigger than 0, and they get gradually bigger and bigger and bigger. And then at some point, presumably right here at 0, they change and they start to get less steep, and they go back gradually to 0. Now on the graph of f prime, that's going to look like this. Starts at 0, and then right around when x is equal to 0, it maxes out, and then the slopes of the tangent lines go back down to 0. Right. Then here, from here on, the slopes of the tangent lines get negative again. So starting with just a little bit smaller than 0, and then gradually larger, the rest of the f prime graph sketch will look like this. Now, here's an opportunity for you to try this on your own. Here's another graph. Follow the steps from the previous slide. Pause now. First things first, draw the xy plane, label the axes, x and f prime of x, and then identifying where the graph has horizontal tangent lines. That would be here, again here at 0, and here, and then drawing in the corresponding points on the f prime graph. Remember, this means that if the slope is equal to 0, then f prime is also equal to 0. So that'll be here, here, and here. Then looking to see what's happening on either side. Are the slopes positive or negative? Well, these slopes will be positive. These slopes will be negative. These are positive, and these are negative. This means that for all of the x values from here back are going to be positive or above the x-axis. So this part of the graph will look like this. And then these are negative, so therefore the y values will be negative. Start at 0, and then go down and back up to 0. It'll look like this. And the thing to know about this is that, well, maybe it's more appropriate to have drawn it down more like this, more exaggerated. And because it's a sketch, we don't really know because we don't know anything about the numeric values of these. So as long as you're going from 0 down and then back to 0, then you're fine. Now, what I will say about this is that because of the symmetry of the graph, whatever you choose for this one, make it look as similar as you can on the other side. And then these are negative. Therefore, I'll just continue this downward past the 0 down to negative infinity. I'll build on the first two examples in example 3. This is what the graph looks like. And again, making a big deal over getting into the habit of checking that this is an f of x graph. And starting again by drawing the xy plane directly below x, f prime of x. And now the only place on this graph where the slope of the tangent line is 0, exactly 0, is here. I'll put the point in on the f prime graph. And then seeing that the slopes of all these tangent lines are negative and the slope for all of these tangent lines are positive, I'm not going to jump right to that. I want to look to see what's happening here, and specifically here. These go from 0, and then they get larger and larger, and at some point they start to taper off. And this goes back down and starts to get flat, but it'll never actually get to 0 based on this pattern, but it will get close to 0, but staying positive. So therefore, the graph on this side of f prime will look like this. So it starts from 0, it peaks, and then it tapers off, staying positive the whole time. And that's going to be the same thing on this side. The slopes go from 0, they peak, and then they taper off back towards 0, but staying negative the whole time. And that'll look like this. And again, if you were drawing a graph like this, try and make, because of the symmetry in F, try and make this look relatively symmetrical as far as the peaks on each side of the y-axis. In example 4, take the time to put this in your notes, going through the point 0, 1, 2, 3, 3, 0, 4, negative 3, and 6, 0. Then connect those with straight lines. Starting with the plane x and f prime of x. Now, because these are straight lines, we're going to actually, instead of sketching this, we're going to actually have as a final product the actual graph of f prime. And that's because in this case, we know what the slopes are exactly for each of the 3 parts of this graph. Now, unlike the other graphs, these aren't going from, the domains are not going from negative infinity to positive infinity. The domain here is from 0 to 6. Therefore, I'll label the x-axis accordingly. I'll fill in the numbers as I go along. And looking at the first part, going from 0 to 2, the slope here, if you look at this, maybe either you take the 2 points and you get the slope with change in y over change in x, or you can just do rise over run, 2 over 2. So the slope here would be positive 1. Well, that means that here, the slopes are going to be for x is equal to 0 to x is equal to 2, not inclusive, more on that in a minute. But the slopes will all be 1. In other words, I'll put a horizontal line here to denote the slopes from 0 to 2. Now, notice I didn't go all the way across, and like I left a little space here and here. I'll talk about this one first because you've seen this one before. There's a corner here, and therefore that means that x is not differentiable at 2. So I'll put a closed circle here. And because there are no x values on the other side, that's going to make this endpoint not differentiable as well. So I'll put an open circle here. Next, determining the slope of this line, so we can figure out what's happening from 2 to 4. Well, rise over run, it's down 3 over 1. So the slope from here to here is -3. And starting off for the same reason that it wasn't differentiable here, I'll put an open circle at 2 comma -3. And also, it's not differentiable at x is equal to 4. Therefore, I'll put another open circle, and then I'll connect the dots again with a horizontal line, right? Because anything between 2 and 4, not inclusive, has a slope of -3. Slope, rate of change, therefore derivative. From between 4 and 6, oops, oh, okay, fine. So between 4 and 6, the slope 3 over 2, positive. So therefore, this is between 1 and 2 because 3/2 is 1.5. So I'll put that right in here, halfway between 1 and 2. And then following this across, I'll start with the open circle at x is equal to 4. I'll put in the other open circle for the other endpoint at 6, and then horizontal line. So this looks very different from the other ones, but the graph looks very different of f than the other two f graphs that we looked at. In order to work in the other direction, it's important to understand the relationship between the f graph and the f prime graph. Notice that when the slopes of the tangent line are positive, what's also happening here is on this interval of the graph, it's increasing. Whereas when the slopes of the tangent line are negative, or when the derivative is negative, then that's where the graph is decreasing. I'll say that formally now. On the previous slides, a graph of f was given, and it was shown that an f prime could be constructed from that f graph. And in this section now, a graph of f prime is going to be given. And then from f prime, conclusions can be drawn about f. We'll also see how to sketch f from f prime. Now for this new random f prime, and notice that here, that even though this says y on the y-axis, it's defining y as f prime of x. Then remembering that when f prime is positive, that means that the slopes of the tangent line are positive on f. And I just showed you that that is where f is increasing on the graph. Likewise, when f prime is negative, like it is here, it's positive here and here, then this is the part of the graph from -1 to 1 where f is decreasing. Takes a little bit to get used to this, so if you don't see it right away, give yourself a little time, practice with it, go over it over and over. Right. Now, a large positive slope means that f is increasing greatly, whereas a small positive slope means that f is increasing only slightly. And now making the connections about what happens when the slope is exactly 0, see how these happen at the peaks and valleys on the graph. In other words, the slope of the tangent line is 0 at the mins and the maxes. And I'll say that formally. When f prime is equal to 0, then at that value of x, there can be either a local max or local min. I'll explain the asterisk in a minute. All right. So let me just show you the graph of f based on this f prime that you're seeing right now. It looks like this. And see how here the y value is 0, and therefore when f prime changes from positive to negative like it is here, see how to the left of this the slopes are positive because f prime is positive, and here f prime is negative, then that's going to result, as you can see from the graph, in a max being right here at x is equal to -1. You can see this, the max here on the original graph. Now here at x is equal to 1, the other place where the derivative is 0, now when f prime changes from a negative to a positive like it does here, watch, these y values are negative, these y values are positive, it's going negative, 0, positive, and see from the graph that that results in a minimum at x is equal to 1. Next, I'll talk about what f double prime says about the original f graph. F prime tells you the behavior of what's called the concavity of the f graph. And I'll say that when f double prime is positive, that means that f is concave up. And what it means to be concave up is the graph is kind of shaped like a smiley face. It's like up, it's happy. And when f double prime is negative, that indicates that f is concave down for whatever that interval is. Concave down looks like this. Literally looks like a sad face. It's down. And when f double prime is equal to 0, well, at that value of x, and it'll be an individual point, not an interval, then that's where f has what's called an inflection point. The graph that I'm showing you now is a graph of some function. This is not an f double prime of x graph. And you can see that right here is the inflection point, because up until here, this part of the graph is concave up, and then it changes, this part of the graph is concave down. Now, other conclusions that you can make from f double prime, you'd say that when f double prime is positive, that means that f prime is increasing. Likewise, when f double prime is negative, that means that f prime is decreasing. And now that you know these things, you could be asked to sketch the graph of f given certain conditions. I'll put all the conditions here first so you can get them into your notes, and then we'll sketch the graph. First condition, f prime is positive on the interval of -infinity to 1, not inclusive. F prime is negative on the interval of 1 to infinity. You're also told that f double prime is positive on two intervals. First one, -infinity to -2. Second interval from +2 to infinity. F double prime is negative on the interval of -2 to 2, all non-inclusive. You're also told that the limit as x approaches -infinity of f of x is -2, and the limit as x approaches positive infinity of f of x is equal to 0. I'll start off with the plane, x, f of x, And I'll label the x-axis with eventually with the pertinent points, 1, -2, and +2. And I'll start here at 1. Then this first set of conditions is saying where f is increasing and decreasing. It's going to be increasing here and decreasing here. And I'm going to denote that on the graph with kind of like a stick figure of the situation. F prime is positive from -infinity to 1, then the graph is going to look something like this. This is the general direction. It's increasing. And then from 1 to infinity, f prime is negative, therefore f will be decreasing. Another way to look at this is that on -infinity to 1, all of the slopes of the tangent lines are positive, and from 1 to infinity, all of the slopes of the tangent line are negative. The second set of conditions deals with negative and +2. I'll draw them in. -2, +2, and this is talking about concavity. This is saying that f is concave up from -infinity to -2. In other words, here. And I'm going to be careful when I draw this that it's also increasing. So it's concave up and increasing as per this. And it's also concave up from 2 to +infinity. 2, negative, and decreasing would look like that. And it's concave down between -2 and 2. Let me draw the inflection point here. So then from -2 to 1, it's going to be increasing and concave down. And then from 1 to 2, it's still going to be concave down, but now it starts decreasing. Seeing what's happening at the endpoints, if the limit as x approaches -infinity of f of x is going to be -2, then that means, as you saw previously, this means that there's a horizontal asymptote of y is equal to -2. I'll draw that in, and that allows me to finish this part of the graph. Just put an arrow here. And then as x approaches +infinity, f of x is going towards 0. So that implies that there's another horizontal asymptote here at y is equal to 0. And I'll put an arrow here to finish off the graph. Here's a pre-printed version of that graph. Notice how they didn't put in the horizontal asymptote at y is equal to 0. But alas, it's there. And I'll use this graph of f prime to sketch a graph of f. I'll start off same way as always. I'll put an xy plane lined up with the x values on the other graph. I'll label this. Here's x. This will be f of x. And I'll label the x-axis. At least I'll put the tick marks for now. And then first thing I'm going to do is find on the f prime graph where either a local min or local max is. Now, careful, because you might want to say that they're at the peaks and valleys, but remember that this is f prime. The mids and maxes for f are going to be where f prime is 0. That's here, here, and here. And I've shown you already how to determine if these are mins or maxes. Remember that a min will be where we're going from negative to positive, and maxes are when the graph is going from positive to negative. Therefore, at x is equal to 1, because the f prime graph is going from negative to positive, then that means that there'll be a min on f at 6, it's going from positive to negative. That means there'll be a max on f. And at x is equal to 8, there'll be a min. Now put 1, 6, and 8 into the graph to represent the minimums and maximums. And then step 2, you want to identify from f prime where f is increasing versus decreasing. And remembering that when f is increasing or decreasing, f prime is positive. So therefore, working backwards, when f prime is positive, that means that f is increasing. So now we can say from 0 to 1, because this is below the x-axis, in other words, f prime is negative, that's when f prime is negative, therefore that's when f is decreasing. So I'll put a stick figure in to represent that from 0 to 1. Then now from ignoring all the peaks and valleys again, between 2 and 6, f prime is positive. Therefore, that means that all of the slopes of the tangent lines are going to be positive, and in turn, that means that f is increasing between 2 and 6, wherever f prime is positive. Likewise, between 6 and 8, f prime is negative, therefore f is decreasing, and then again from 8 to 9, f prime is positive, therefore f is increasing. Next, determining the concavity of f. As I mentioned on the previous slide, when f prime is increasing, f is concave up. Here we get to see an example of that. And let me just say this first. Also, regarding concavity of f, when f prime is decreasing, then f is concave down. Now looking at this graph, where is f prime increasing? Well, from 0 to 2. I'll put 2 in here on the graph. Therefore, we can say that from 0 to 2, f is concave up. So I'll just kind of, more information, I'll just fill that in. It'll look like this. That's going to make an inflection point at 2. And then decreasing from 2 to 3, that means that f is concave down. Here, get another inflection point. From 3 to 5, f prime is increasing, therefore f is concave up, but still increasing. And then decreasing from 6 to 7, and I'll just put 4 in here for completion. That means that here's another inflection point. It's concave down. And then concave down to here. Here's the inflection point. And then concave up the rest of the way. So seeing what happens here just naturally as we take into account increasing, decreasing, and concavity, see how naturally there's a min at 1, there's a max at 6, just like we expected, and there's a min at 8. Two things. Previously I said that this was decreasing from 6 to 8, I said 6 to 7, I meant to say 5 to 7. Also, a common question here is how did I know to make all the y values in f positive? And the answer to that is I don't know. It's just something that I've chosen. There's nothing to say that I couldn't have drawn my stick figures for increasing and decreasing both above and below the x-axis or completely below the x-axis. It's absolutely arbitrary. Fortunately, this is the end of the graphing section for this week. And in addition to the homework, I'll also put out a worksheet for you to try more of these on your own. Lumen doesn't do a great job covering this as far as giving good examples for you to practice. And really, that's the only way to get good at these is to practice. I like to say that math is not a spectator sport. And this is definitely no different. So I'll put a worksheet up. I'll put it under week 5 material under resources on Blackboard. And then any questions that you have on it, you can go over it with your recitation instructor. Something else to note is that on the curriculum, I tweaked it. For some reason, product rule wasn't on there. So that's something that we are going to cover this week. But I decided to move, since the graphing is a lot, I decided to move the derivative for trig functions to next week. So definitely check out the curriculum to see those minor changes. This definitely, if you try to take a break, well, because I doubt you watch these all the way through, this is definitely a good time to take a break. As I said before, the definition of the derivative, all the calculations to do average velocity versus instantaneous velocity, to learn about limits. A lot of that, the calculations are very cumbersome. I feel like this part of the course is like a breath of fresh air, comparatively speaking. I'm going to start by, again, bringing all those concepts together in one place. F prime of x is the same thing as the derivative, which is the same thing as rate of change, which is the same as the slope of the tangent line. And this is all the same thing as instantaneous velocity. And I'll say that derivative can be measured using the slope of the tangent line at some value of x. And until now, we've been finding the slope, or f prime of x, using one of the two definitions of the derivative. First one was f prime of some constant a, limit as x approaches a, of numerator f of x minus f of a over x minus a. And as I said, where a is a constant of x. And I showed you how this is approximately like slope because it's approximately y2 minus y1 over x2 minus x1, where x1 and x1 y1 and x2 y2 are points on the curve. And the second definition of the derivative, f prime of x, this is more generalized. We have the limit as h approaches 0 of f of x plus h minus f of x all over h, where h is the distance between the two values of x. Now, there's a new way to differentiate. So there are a number of rules. We call them rules. The first rule, the easiest one, is the power rule. You would use the power rule when you have something in the format of a power function. A power function is in the format of a times x to the n. And where do we generally see this? In monomials, polynomials. It's the derivative with respect to x of this power function, a times x to the n. Remembering that a is a coefficient. Then the formula for this would be to take this power and bring it in front. So we have n, we keep the coefficient, it's n times a, and then whatever this power is, you drop it down a power. So then the x to the n becomes x to the n minus 1. And just looking at the other notation, the derivative with respect to x of f, this is the same thing as the notation f prime of x. You know that, I'm just reminding you. For example, if f of x is, you can see this is in power function format, 4 times x cubed, then the derivative of 4x cubed, following the rule, bring the 3 in front, times 4, and then dropping this down a power, it would be x to the 3 minus 1. Then you'd simplify this. 3 times 4 is 12. 3 minus 1 is 2. So this becomes x squared. Right? And likewise, if you're given f of x and you're asked to find f prime of x, then a way that you can write this is 4x cubed prime, and then you follow the power rule, simplify, and it becomes same thing. Again, it's just different notation. Derivative is 12x squared. I rewrote this for you to reference. And from here forward, I'm going to interchange between Newtonian notation and Leibniz notation. If you're asked to find the derivative of x cubed, well, there's an implied 1 in front, so I'd bring the 3 in front, 3 times 1, drop this down to power, x to the 3 minus 1. This simplifies to be 3x squared. And I'll give you some special cases. This is one of them, because there'll be ones that you'll just end up using so often that you'll just memorize. You're going to come to find out that this is 1, and you'll see why in the next example. If you're asked to find the derivative of 2x, then this is really just 2 times x to the first power. So now you know what n is. So if you bring 1 in front, it's 1 times 2, and then the power is x to the 1 minus 1. Let me see, I simplified this. This is just 2. And then this becomes x to the 0 power. And, well, of course, you're going to simplify that. You know that anything to the 0 power is 1. Therefore, 2 times 1 would be 2. I'll get back to this in a second. The next thing to know is that if you're taking the derivative of a function times a constant, then its equivalent would be to take the derivative of the function and then multiply the constant into the derivative after the fact. Now, if we know that x prime is equal to 1, then we can think of this, we can look at this from a different angle. We can think of 2x prime as 2 times x prime. Again, just taking the constant and bringing it out in front and just taking the derivative of the variable. And then 2 would just get multiplied into x prime, which we know is 1. So therefore, again, the derivative of 2x is 2. Here's another special case. The derivative of 5, I'll put 5 in power function format. It's technically 5 times 1, which I can write as 5 times x to the 0, based on this fact. And then when I take power rule, the 0 comes in front. It becomes 5 times x to the 0 minus 1, but this is irrelevant here because 0 times this whole thing is just going to make this all 0. And that's going to be the case for any constant. Therefore, I'll say that the derivative of a constant is 0. These are all the rules that you've learned so far. You have power rule in general, derivative of x, derivative of a constant, and even this fact. It's not a bad idea to start making a sheet or an index card with all your derivative rules on them. Continuing with the power rule, next I'm going to show you some more complex examples, because sometimes a function is not given in this power format, but it can be easily manipulated to be put in the power function format to be able to use the power rule. First example, 3x to the 10th over 5. First thing to do is to have a dedicated a. So all you would have to do is take the 3/5 and put it out in front. And now it's in that a times x to the n format. And then taking the derivative, 10 goes in front, and starting to get a little more streamlined, because when it gets to the exam, you don't need to show 10 minus 1. You can certainly do that in your head. So this becomes x to the 9th, and you're going to be expected to simplify fractions when it's appropriate. 10 over 5 becomes 2, 3 times 2. Final derivative is 6 times x to the 9th. Next example, taking the derivative of 1 over x. You're assuming that this is x to the first power, and then using exponent laws, you're going to bring this up into the numerator by negating the exponent. Now you're taking the derivative of x to the negative 1, a is 1, n is negative 1, and then using power rule, it becomes negative 1 times x to the, and when you're dealing with negatives, it's not a bad idea to write this out if it's going to help you to see it correctly. Minus 1 minus another 1 is negative 2. And a lot of times they'll ask you to write this as a positive exponent. So again, using your exponent laws, you're going to put the x to the negative 2 back down into the denominator by making the exponent positive. Final derivative, negative 1 over x squared. You're going to use exponent laws again here for the square root of x, remembering that this is x to the 1/2, and now this is in the proper format to use power rule, becomes 1/2 x to the 1/2 minus 1, and I'll bring this, you'll eventually do this in your head, maybe for the first few times when you have to drop down a power with a fraction, you'll just bring this off to the side and do the work. Getting a common denominator, this becomes 1/2 minus 2/2. 1 minus 2 is negative 1. So this becomes 1 minus 1/2 is negative 1/2. Right? And again, turning this into a positive exponent, and I'm even going to take it one step further. Watch. This is going to become x to the 1/2 in the denominator, and then I'll rewrite it as a radical. So the derivative of square root of x is 1 over 2 times radical x. And just a side note, square root of x, this is something that if you're a memorizer, some students will memorize this, that the square root of x's derivative is just 1 over 2 radical x. That's your choice. Now a different kind of radical, cube root of x squared, writing this as x squared over 3, or x to the 2/3. Now it's in power function format. The derivative becomes 2/3 x, and show yourself that 2/3 minus 1 is negative 1/3. And then simplifying it, it becomes 2 over, and I'm just putting the x with the 3 in the denominator. Final derivative is 2 over 3 times the cube root of x. As we get into the other rules, you'll probably use product rule for something like this, but if you didn't see product rule in any calculus course that you've taken in the past, then the way to solve this is, again, using exponents. Exponent laws are definitely our friend here. And recognizing that they're the same base. This is x to the first, this is x to the 1/2, and then combining these, you're adding the exponents. 1 plus 1/2 is 3/2. Again, pause and show that to yourself if you don't readily see that. And now this is ready to have the derivative taken to it. 3/2 comes in front. 3/2 minus 2/2 is 1/2. And final answer, again, you can write it like this, or just to give you some options, you can leave the 3/2 in front and then have the radical x off to the side. Right? Again, nothing to say that you couldn't have written this like this. Again, I try and give you some different options. Both are full. I would accept both of these as full credit answers on an exam or on a quiz. Here's one for you to try on your own. Notice the different instruction. Instead of ddx or whatever prime, it's using the verb differentiate. Remember that differentiate just means to take the derivative of the function. Pause now. Here's the solution. Start by putting this in power function format. This becomes x to the -2. And then the derivative would be -2 times x to the -3 when you drop this down to power. And then making the exponent positive, this becomes -2 times 1 over x cubed. And again, you have the option of writing this as one fraction. The next example is going to start to bring concepts together, taking this to the next level. Instead of just asking you to take the derivative, you're being asked to find the equation of a tangent line to the curve y is equal to the 4th root of x, and you're given the ordered pair 1, 1. Now, remembering that to get the slope of this tangent line, well, that's the same thing as the derivative of y at the particular point. Now, y prime, I'm going to use power rule to find the derivative of the 4th root of x, writing it first as x to the 1/4, and then taking the derivative becomes 1/4 times x to the -3/4. And I'm going to have to plug 1 into this, so I want to make this a little more plug-in friendly. Therefore, I'll write this as 1 over x to the 3/4, to the positive 3/4 specifically. Now, remembering that this is the general slope, right, for any point on the curve. Specifically, we want to find out what's happening at the point 1, 1. So I'll find the slope at 1, 1. I don't really technically need the y, but just being consistent. Right? That means that I'm plugging x is equal to 1 into here, 1 over 4 times 1 to the 3/4. And sometimes people, their brains just kind of fade when they have to go evaluate something like this. Just remember that 1 to any power, 1 to any root is just 1. So this becomes 1 over 4 times 1, which will just simplify to 1/4. And now, finding the equation of the tangent line, now that we have the slope at this point on this curve, using the point slope formula, y minus y1 equals m times x minus x1, plugging in 1 for y1, 1/4 for the slope, and then x minus 1, and then simplifying this, distributing 1/4 x minus 1/4, then adding 1 to both sides, combining this. This works out to be positive 3 over 4. And this is just an aside. A normal line is just perpendicular to a tangent line. And to find the normal line, you're going to take the negative reciprocal of the slope, just basically the definition of perpendicular. And therefore, and don't worry about changing the intercept. The normal line here to this tangent line would just be y is equal to -4x plus 3/4. So far, the examples that I've shown you have been with monomials, but power rule works on polynomials also. Let me show you the logistics of this. If we consider each of the monomials their own separate function, then when you go to take the derivative, you could just take the derivative of each term applying power rule. In other words, take the derivative of f of x, and then it will be plus the derivative of g of x. For example, to take the derivative of x to the 4th minus 6x squared plus 4, then technically what you're doing is taking the derivative of x to the fourth, subtracting off the derivative of 6x squared, and then plus the derivative of 4. Now, each of these individual pieces is exactly what we've been doing so far. And then taking each derivative of x to the fourth is 4x cubed, and the derivative of 6x squared becomes 12x. Derivative of a constant is 0. And simplifying this, because of course we're not going to write 0 in the final answer, then this derivative would be 4x cubed minus 12x. Go ahead and practice this for yourself. Think about how you would handle this with pi, taking the derivative of x to the 8th plus 12x to the 6th minus 4x to the 4th minus 6x plus pi. Pause now. And something to know is that this step is more to illustrate the theory, and you don't need to show this line of work when you're taking a quiz or an exam. So the answer to this, you can go right from here to here, and maybe you're taking a step in between. You're writing 6 times 12 times x to the 5th and then simplifying it. I'll leave that up to you to see what you think is appropriate for your work. I recommend you show that work because this way, if you made a calculation error, it would be a more minor deduction. We can follow your work. The derivative here would be 8x to the 7th plus 12 times 6 is 72, x to the 5th, 4 times 4 minus 16, x cubed. This just becomes minus 6, and as per the hint that I gave you, derivative of a constant is just 0, so it drops out in the derivative. Now, revisiting about velocity, acceleration, position, remembering that s of t is position, v of t is velocity. Velocity is also the derivative of position, s prime of t. A of t is acceleration and can also be considered v prime of t and also s double prime of t. Now, if you're given a position to be s of t equals 2t cubed minus 5t squared plus 3t plus 4, and you're asked to find the velocity and acceleration, and you're given units. The units for position is centimeters. Time is in seconds. Then to get velocity, all you're going to do is use power rule on this. V of t would be 6t squared minus 10t plus 3, and then technically plus 0. Now for the units, remembering that the derivatives units are the y units over the x units, this would be centimeters per seconds. For acceleration, you would just take the derivative of the velocity, because you know that it's velocity prime. It would be 12t minus 10, and then the units would be centimeters per second, and then seconds, because you have velocity units divided by the x units. And then simplifying this, this would just be centimeters per seconds squared. Follow-up question could be, what is the acceleration after 2 seconds? All you would have to do is, this is time, just plug 2 into t. In other words, you want to get a of 2. That would be 12 times 2 minus 10. 24 minus 10 is 14. Don't forget to put units, centimeters per seconds squared. So the thing to know is that power rule is only used with power functions. Next, I'm going to show you other functions that are not power rule and how to take their derivative. And I'm going to start with the exponential function. Specifically, I'm going to talk about e to the x. The derivative of e to the x, and this is the only function that this happens for, is itself. The derivative of e to the x is e to the x. And again, I can't stress this enough. Do not use power rule for this. The derivative is not x times e to the x minus 1. And for now, this is the only exponential function I'm going to talk about. I'll talk about other exponential bases later on in the course. And going right to an example, if you're given a function to be e to the x minus 2x squared, and you're asked to find f prime of x, and we'll work with some higher order derivatives too for practice. So let's also find f double prime of x and f triple prime of x. Now for f prime of x, e to the x, just deal with this a term at a time, will just be e to the x. And then for minus 2x squared, that's just going to be power rule. This will be minus 4x. And then to get f double prime, just taking the derivative of f prime, e to the x stays e to the x. And again, applying power rule, negative 4x, the derivative is minus 4. And then third derivative would just be e to the x, because when I take the derivative of a constant, this zeroes out. And just to review, so far you've learned that the derivative of a power function, right, for a single term, a times x to the n, is n times a times x to the n minus 1 power. And for multiple terms, you learn that to take the derivative of, let's say, a times x to the n plus b times x to the m, because these could have different powers and different coefficients, then all you would do is take the individual derivatives of each term. Right? And also so far, you've seen that the derivative of e to the x is itself. Now, you might also guess, based on this, that the derivative of a product of functions, in other words, the derivative of f of x times g of x, is the product of their derivatives. And you would be wrong. And let me show you why. If you're given that f of x is equal to x and g of x is equal to x squared, then f prime of x is 1, g prime of x is 2x. And by this faulty thinking, then the derivative of x times x squared would be 1 times 2x, which is 2x. Right? But if you multiply f of x times g of x from the get-go, you'd have x times x squared, which would be x cubed. And then if you took the derivative of x cubed, you'd see that this is 3x squared, which is not 2x. So this is not correct. The theory behind product rule can be shown using a rectangle. Let's say this rectangle has length of f and width of g. Then the area of this rectangle, and for now I'm going to call it a sub 1, go with me on this, then the area of this rectangle would be f times g. Now, if you took this rectangle and stretched it, let's say we lengthened both the length and the width, then the new resulting rectangle would look something like this. Now, here's the rectangle that we originally had, f times g, and then how much f changed and how much g changed, we could represent those as delta f for how much f changed, and then delta g for the change in g. Then the area for the new rectangle, I'll call that a sub 2, would be length times width, or f plus delta f, times g plus delta g. And if we wanted to find the area of just the part of the rectangle that changed, and I'll highlight that, then we could get that area by just subtracting the two, like finding A2 and then subtracting off A1, this piece right here. Right. Now I'll call this grayed out area, the changed part of the rectangle, I'll call that A delta. And as I said here, we would get that from doing A2 minus A1. A2 being F plus delta F times G plus delta G minus A1, which is F times G. I'm going to simplify this. I'll start by foiling the binomials. The result will be F times G plus F times delta G. And I'll write this next one as G times delta F. And then the last will be delta F times delta G. And I'll bring down the minus F times G. These are like terms, so the FG's will cancel out. And I'll write the change in area a different way. I'll write it as delta F times G. In other words, how much this has changed. And then I have 3 terms left. I'll just copy them back down. F times delta G plus G times delta F plus delta F times delta G. The next thing to do is to make these functions with respect to x. So I'll divide through by delta x, each of the terms on both sides of the equation. That'll make the left side delta F times G divided by delta x. Then the first term on the right will be F times delta G over delta x. Then G delta F over delta x plus delta F delta G over delta x. I'm trying to turn this into something that's related to derivatives. So I'll take the limit as delta x goes to 0 of delta y over delta x, then that becomes, as we've seen, dy dx. I'm going to apply this thinking to the equation that we've been creating. So if I take the derivative of f times g, right, see I'm just changing the delta, f times g over dx, then on the right side I'm going to split out the f, and then delta g over delta x becomes dg dx, so it's f times dg dx. I'll do the same thing with this one. It becomes g times df dx, right? Again, I'm just taking the limits on all of these. The limit as delta x goes to 0. And watch what happens with this one. If I break it out the same way I broke these out and separate the delta f into its own factor, then when I take the limit, like as delta x goes to 0, this now is not a function like these are. This is just like a constant. So as delta x goes to 0, delta f will naturally go to 0 also. And that'll make this 0 times this times essentially dg dx. So this whole thing, that whole term is just going to go to 0. So now we just have this, and this is going to become the product rule. And this is just rewritten from the previous slide. d dx of f times g is equal to f times dg dx plus g times df dx. And let me just say formally, when two differentiable functions are multiplied, you'll use the product rule in order to take the derivative. I'm going to give you a shortcut for this, more of like a memory tool. If I use prime notation, I'll have f times g prime, and I'm making a big deal out of this because part of taking the product rule is recognizing that you have multiplication and noticing that product rule is appropriate. So f times g prime, and I'm going to just, for the memory trick, I'm going to just switch these terms around. So df dx becomes f prime, so this becomes f prime times g and then this becomes f times g prime. So it kind of flows. It's f prime g plus fg prime. That's what you'll memorize. I'm going to write these up formally in both notations with respect to x, so just a little more formal from what's here. F of x times g of x prime is equal to f prime of x times g of x plus f of x times g prime of x. And then in Leibniz notation, it'll be the derivative with respect to x of f of x times g of x, and this is going to become d dx of f of x times g of x plus f of x times d dx of g of x. And now, at last, we're ready for an example. You're asked to find the derivative of h of x equals x times e to the x. The strategy for this is that you're going to build a chart of the two functions and their corresponding derivatives. That's going to make it easy for you to plug into the formula. And it's also going to minimize your chance of making a mistake, because these are going to be easy derivatives to take. As we get down the road, you're going to start taking more complex derivatives, and it's going to be really important for you to keep your work organized. Now, if this is x times e to the x, that means that the first, if we have an f times a g, then x is going to be the f of x, and then the g is going to be e to the x. And I'm being formal here the first time. I'm going to streamline some of this in the next examples. Right? So we have f and g defined using power rule. F prime of x is going to be 1. G prime of x, of course, is going to be e to the x. And now that I have all of the components, h prime of x is going to be, and I'm just rewriting what's here, it's going to be f prime of x times g of x plus f of x times g prime of x. Now it's just a matter of plugging in. F prime of x is 1, g of x is e to the x, f of x is x, g prime of x is e to the x. And I'll simplify this. This will become e to the x plus x e to the x. Rewriting the formulas in both notations. Now you're asked to find the derivative, and again I'm calling it h of x equals, first factor is x squared plus 3x, and it's times 5x cubed minus 2. Here's f of x, here's g of x, and again streamlining this, and I'll just call this f to x squared plus 3x, g is 5x cubed minus 2, and then taking their corresponding derivatives, f prime will be 2x plus 3, g prime will be 15x squared. Therefore, h prime of x will be f prime g plus f g prime. And then plugging in, f prime 2x plus 3 times g, 5x cubed minus 2, plus f, which is x squared plus 3x, times g prime, which is 15x squared. Now, the beauty of this is that you don't have to simplify this at all, just leave it in its factored form. And as promised, here's one that's a little more complex. You're asked to differentiate f of y equals 1 over y squared minus 3y to the fourth times y plus 5y cubed. F will be 1 over y squared minus 3y to the fourth, and g will be y plus 5y cubed. Now in this case, I'm going to manipulate this a little to make it more derivative friendly. I'll write 1 over y squared as y to the negative 2 minus 3y to the fourth. And then I'll use power rule. The derivative of y to the negative 2 is negative 2 times y to the negative 3. Make sure you see that. And then the derivative of negative 3y to the fourth will be negative 12y cubed. And then writing this as a positive exponent, the derivative of f becomes negative 2 over y cubed minus 12y cubed. Just box these. This just becomes 1 over 15y squared. Box those as well. Now f prime of y is equal to f prime, which is negative 2 over y cubed minus 12y cubed, times g, y plus 5y cubed, plus f, 1 over y squared minus 3y to the fourth, times g prime, 1 plus 15y squared. And again, just leave this as is in its factored form, all positive exponents. This is the answer. Here's one for you to try on your own. You're asked to differentiate f of x equals 4x cubed minus 6x squared plus 1 times 5x to the fourth plus 7x squared plus 3x. If you're looking at the PDF of the slides, you'll see that there are actually two problems. Just do the first one for now. Pause. Calling the first factor f and the second factor g, then f prime will be 12x squared minus 12x. And if this is g, then g prime will be 20x cubed plus 14x plus 3. And that'll make the derivative of f prime of x be, just label this f prime times g plus f times g prime. In other words, 12x squared minus 12x times 5x to the fourth plus 7x squared plus 3x plus 4x cubed minus 6x squared plus 1 times 20x cubed plus 14x plus 3. And then for the second example, you're asked to find f prime of x, where f of x is equal to x plus radical x plus the cube root of x, that's all one factor, times e to the x minus x squared is the second factor. And again, pause now. Since this is the first factor, which I'm labeling as f, before I take the derivative, I'm writing this in power format. It becomes x plus x to the 1/2 plus x to the 1/3. And then the derivative will be 1 plus 1/2 x to the negative 1/2, or maybe you memorized that fact and just went right to 1 over 2 radical x. And then x to the 1/3 prime is 1/3 times x to the negative 2/3, which when I rewrite this as a positive exponent and then as a radical, it becomes 1 over 3 times the cube root of x squared. G is e to the x minus x squared, a comparatively easier derivative to take. Then g prime, I'm just line these up, will be e to the x minus 2x, and then f prime of x, which is completely different from these two. These are just labels. F prime of x is equal to f prime times g plus f, and I'm just, in the interest of space, just writing this on the second line, times g prime. And this is 1 plus 1 over 2 rad x plus 1 over 3 times the cube root of x squared times e to the x minus x squared plus x plus radical x plus cube root of x times e to the x minus 2x.